A lightning protection system installed on a tree to protect it from lightning damage is generally not required to be connected to the electrical service grounding system of a nearby home. The primary goal of a lightning protection system on a tree is to safely conduct lightning strikes to the ground, minimizing damage to the tree itself and reducing the risk of ground current surges affecting nearby structures. Connecting it directly to the electrical service grounding system of a house can inadvertently introduce lightning energy into the house's electrical system, potentially damaging sensitive electronics and creating a fire hazard. The National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems within buildings and structures, but it doesn't specifically address lightning protection systems for trees. However, general principles of grounding and bonding apply. A dedicated grounding system for the tree is recommended. This typically involves driving one or more ground rods into the earth near the base of the tree and connecting the lightning protection conductors to these ground rods. The depth and number of ground rods should be determined based on soil conditions and local electrical codes. The grounding system should provide a low impedance path for lightning current to dissipate into the earth. The distance between the tree and the house is also a factor. In the question, the tree is 30 feet from the home's electrical service. This distance provides some degree of isolation, reducing the likelihood of direct current transfer between the tree's grounding system and the house's grounding system. However, it's still crucial to ensure that the grounding system for the tree is properly designed and installed to minimize the risk of ground potential rise, which could indirectly affect the house's electrical system. Considerations include, firstly, soil resistivity. High soil resistivity increases the impedance of the grounding system, making it less effective at dissipating lightning current. In areas with high soil resistivity, multiple ground rods or other grounding enhancements may be necessary. Secondly, equipotential bonding. Equipotential bonding involves connecting various metallic components and systems to create a common ground potential. This helps to minimize voltage differences and reduce the risk of electrical shock or damage during a lightning strike. While direct connection to the house's electrical service grounding system is generally not recommended, equipotential bonding between the tree's grounding system and other nearby metallic structures, such as fences or underground utilities, may be beneficial. Thirdly, surge protection. Surge protection devices, or SPDs, are designed to protect sensitive electronics from voltage surges caused by lightning strikes or other electrical disturbances. SPD should be installed at the electrical service entrance of the house and at other critical locations to mitigate the risk of damage from lightning-induced surges. While a lightning protection system on a tree can help to reduce the overall risk of lightning damage, it's not a substitute for proper surge protection within the house. Furthermore, the design and installation of a lightning protection system should comply with applicable standards such as those published by the National Fire Protection Association, or NFPA, specifically NFPA 780 standard for the installation of lightning protection systems. These standards provide detailed requirements for grounding, bonding, and surge protection to ensure the safety and effectiveness of the system. The installation of a lightning protection system should be performed by a qualified professional with experience in lightning protection design and installation. They can assess the specific site conditions, evaluate the risks, and design a system that meets the applicable standards and provides adequate protection. Lightning protection systems typically involve air terminals, also known as lightning rods, which are installed at the highest points of the tree. These air terminals are connected to down conductors, which run down the trunk of the tree and connect to the grounding system. The air terminal should be positioned to intercept lightning strikes and safely conduct the current to the ground. The down conductors should be securely fastened to the tree and protected from mechanical damage. The grounding system should be designed to provide a low impedance path for lightning current to dissipate into the earth. This typically involves driving one or more ground rods into the earth near the base of the tree and connecting the down conductors to these ground rods. The depth and number of ground rods should be determined based on soil conditions and local electrical codes. The grounding system should be inspected periodically to ensure that it is in good condition and that the connections are tight and corrosion-free. Any damage or deterioration should be repaired promptly. In summary, a lightning protection system on a tree does not typically require connection to the electrical service grounding system of a nearby house. A dedicated grounding system for the tree is recommended, and the system should be designed and installed by a qualified professional. Surge protection devices should be installed within the house to protect sensitive electronics from voltage surges. Compliance with applicable standards such as NFPA 780 is essential to ensure the safety and effectiveness of the system. Additional considerations for grounding and bonding include firstly, grounding electrode system. The grounding electrode system is a critical component of any electrical system, including lightning protection systems. It provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. The NEC specifies the requirements for grounding electrode systems, including the types of electrodes that are permitted, the size and material of the grounding conductors, and the methods for bonding the electrodes together. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. Secondly, bonding. Bonding is the process of connecting various metallic components and systems to create a common ground potential. This helps to minimize voltage differences and reduce the risk of electrical shock or damage during a fault condition or lightning strike. The NEC requires bonding of various metallic components, including electrical equipment enclosures, metal conduits, and metal water pipes. Bonding conductors must be sized appropriately to handle the available fault current. Thirdly, ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in certain locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. Fourthly, arc fault circuit interrupters, or SIs. SIs are designed to protect against fires caused by arc faults. An arc fault is an unintentional electrical discharge that can occur in damaged or deteriorated wiring. SIs detect arc faults and interrupt the circuit, preventing the arc from igniting nearby combustible materials. SIs are required in certain locations, such as bedrooms, to provide enhanced fire protection. The NEC also provides requirements for surge protection devices, or SPDs. SPD are designed to protect sensitive electronics from voltage surges caused by lightning strikes or other electrical disturbances. SPD are installed at the electrical service entrance and at other critical locations to divert surge current to ground, protecting the connected equipment. The NEC specifies the types of SPD that are permitted, the installation requirements, and the performance characteristics. Furthermore, the NEC addresses the requirements for wiring methods. Wiring methods refer to the types of cables, conduits, and other materials that are used to install electrical wiring. The NEC specifies the permitted wiring methods for various applications based on factors such as voltage, current, and environmental conditions. The wiring methods must be installed in accordance with the NEC requirements to ensure safety and reliability. The NEC also includes requirements for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. The NEC specifies the types of overcurrent protection devices that are permitted, the ampacity ratings, and the installation requirements. Overcurrent protection devices must be selected and installed to protect the wiring and equipment from damage due to excessive current flow. In addition, the NEC addresses the requirements for electrical equipment. Electrical equipment includes a wide range of devices, such as transformers, motors, and control panels. The NEC specifies the installation requirements for various types of electrical equipment, including grounding, bonding, and overcurrent protection. The equipment must be installed in accordance with the NEC requirements to ensure safety and proper operation. Lightning protection for trees involves creating a safe path for lightning to follow, diverting it away from the tree's internal structures and into the ground. The components of a tree lightning protection system typically include, firstly, air terminals. These are pointed metal rods, also known as lightning rods, installed at the highest points of the tree, typically the top of the main trunk and the tips of major branches. Air terminals are designed to intercept lightning strikes and provide a preferred path for the current to flow. Secondly, DAN conductors. These are heavy-gauge copper or aluminum cables that connect the air terminals to the grounding system. DAN conductors provide a low-impedance path for lightning current to flow from the air terminals to the ground. They are typically routed along the trunk and major branches of the tree. Thirdly, ground rods. These are metal rods driven into the earth near the base of the tree. Ground rods provide a connection to the earth, allowing the lightning current to dissipate safely into the ground. Multiple ground rods may be required to provide adequate grounding, depending on soil conditions. Fourthly, bonding. Bonding involves connecting various metallic components of the lightning protection system together to create a common ground potential. This helps to minimize voltage differences and reduce the risk of side flashes. Bonding is typically done using copper bonding jumpers. The installation of a lightning protection system on a tree should be performed by a qualified professional with experience in lightning protection design and installation. The professional will assess the tree's size, location, and surrounding environment to determine the appropriate type and placement of the lightning protection components. The installation process typically involves firstly inspection. The professional will inspect the tree to identify the highest points and determine the best locations for the air terminals. Secondly, installation of air terminals. Air terminals are installed at the selected locations, typically using clamps or other fasteners that do not damage the tree. Thirdly, installation of DAN conductors. DAN conductors are routed along the trunk and major branches of the tree, using clamps or other fasteners to secure them in place. Fourthly, installation of ground rods. Ground rods are driven into the earth near the base of the tree, and the DAN conductors are connected to the ground rods using bonding connectors. Fifthly, bonding of metallic components. Any metallic components of the lightning protection system, such as air terminals, DAN conductors, and ground rods, are bonded together using copper bonding jumpers. Regular inspection and maintenance of the lightning protection system are essential to ensure its continued effectiveness. The system should be inspected at least once a year and after any major storms or lightning strikes. During the inspection, the professional will check for any damage to the air terminals, DAN conductors, or ground rods. They will also check the connections to ensure that they are tight and corrosion-free. Any damage or deterioration should be repaired promptly to maintain the integrity of the lightning protection system.